Hi, welcome. Today we're going to talk about voltaic cells. Now, we've been talking about oxidation reduction up to now, and just to remind you, oxidation is the loss of electrons by a species and reduction is the gain of electrons. Now, the process of oxidation reduction is not they're not separate events. They happen together because the species that is losing electrons is transferring them or it's giving them to another species that absorbs it, gains them. So oxidation and reduction go hand in hand. One cannot happen without the other. Now, because there is a motion of electrons, the process releases energy, and that energy is released in the form of heat normally. When you have both the oxidation and the reduction taking place in the same place, like for example when we did the enthalpy lab for a redox reaction when we use zinc and the copper 2 sulfate solution, you would recall that the temperature increased quite rapidly. That increase is generated by the motion of electrons, by that process of the oxidation of the zinc and the reduction of the copper. Now, in that reaction, the zinc released 2 electrons to become zinc 2+ ion, and the copper absorbed the 2 electrons to become, the copper ion absorbed 2 electrons to become copper metal. All right. Now, if we can separate the process of oxidation and reduction and allow the electrons to travel through a wire, through some type of conductor, we can generate an electrical current. And that's what a voltaic cell is. It's something that allows us to generate chemically an electrical current. And that's the principle behind all the batteries that you use. All right? Now, as I said, how can we do this? How can we separate the oxidation from the reduction? Well, one of the simple ways that we can do this is to create what are called half cells. All right? A half cell is when we put a metal into a solution of its metal ion. In the case of zinc, if we put zinc metal into a solution of, for example, zinc nitrate, we're going to establish an equilibrium in which some of the zinc metal will lose electrons and become zinc 2+ plus 2 electrons. But similarly, some of the zinc 2+ can find the 2 electrons and become some zinc. So the process is in both directions. If those 2 electrons here combine with this will make some zinc. And of course, it's an equilibrium that is being established. The best way to represent that equilibrium is what we have written here, which is the process of the zinc metal going into aqueous zinc ion plus the 2 electrons. All right. Now, this happens in a small amount, and how can we prove that it happens? Well, experimentally, if you put a smooth piece of zinc into a solution of zinc nitrate and you let it rest there for a while, you'll find that the solution, or the piece of zinc does not gain or lose mass in these conditions, but it does change its surface. Its surface, instead of being smooth, because as the process is happening, it becomes pitted, it becomes irregular, as some areas are losing zinc metal and it is being deposited in different places. It's not going to be deposited exactly in the same place, and so we get that pitting or that roughness occurring. All right? We can do the same process that we did for the zinc for the copper. In the case of the copper, again, the copper metal would establish an equilibrium with the copper ion, all right, by the copper metal releasing 2 electrons into the solution, becoming copper ion. But those 2 electrons, again, can be taken up by some copper ion to become some more, it's not very visible, let me try it with the green, some more copper metal, and vice versa. It can release the 2 electrons out and establish that equilibrium. Now, that equilibrium could be written in this form, but if we recall from the reaction, the first reaction that we had where the zinc reacted with the copper 2 ion, we're going to flip that reaction around to show that the copper 2 ion is actually being reduced as opposed to being oxidized. It is just a formality since we are trying to mimic or try to represent what was happening in the reaction of zinc and copper 2 nitrate or sulfate, which we had earlier in the reaction. Okay, so we are going to use instead the reaction in which the copper 2 ion is gaining electrons to become solid copper metal. Okay, now I've lost my cursor, but we can go like that. We have these two half cells, half cell because they're not a complete cell. An electrochemical cell or a voltaic cell contains those two parts, or we can call them half reactions. You remember when we talked about balancing equations. We have the two half reactions or the two half cells, the oxidation in one side, the reduction in another side. All right. Now, if we actually put a wire connecting, and actually I'm going to move down so you can actually see this in the image. If we were to put a wire conductor between the two electrodes or the two pieces of metal, you would imagine that we could allow electrons to leave the zinc, all right, and travel all the way through the wire and get all the way into the copper and react with the copper 2 ion to make some more copper. So we could imagine that this process could happen and that the electrons are traveling through here, and eventually I'm going to put it into green because otherwise it doesn't show very well. All right, the two electrons join with this to make some copper metal. All right. But the reality is this doesn't happen. If you actually put a voltmeter here in the center and you read as it is currently, it reads 0. And the reason for that is that as you move electrons from the zinc into the copper, the solution, all right, of the zinc is going to do what? How is it doing? It's got the zinc and it comes out as zinc 2 plus, and the two electrons are the ones that are going to travel upwards, right? They're coming out of this. You're going to cause what is called a charge separation. The zinc ion that has been formed is going to make the zinc half cell positive. The electrons that you sent to the copper neutralize one of the copper ions. So you can imagine that this copper ion is no longer there, so you're going to have more negative charge that is not being counteracted by a positive charge. And that is one of the problems, the principles in science that of physics, that the universe does not want charge separation. What would happen if I try to put another pair of electrons? Well, the copper solution is now negatively charged. It will repel the electrons. The zinc solution is positively charged. It would be attracting those electrons, and therefore the electrons do not want to flow in that direction, and so there would be no flow of charge, of electrons. So how do we do this? Well, we have to add one more component. All right, we have to add something that allows the mixture or the cell to remain electrically neutral. So we're going to add what is called a salt bridge. A salt bridge is a glass tube that contains a solution of inert materials, normally some type of spectator ions. In this case, I'm going to use potassium nitrate. all right, because it does not affect the results. And so you put a tube that contains potassium nitrate in solution. And so one side, the nitrate ions are going to flow towards the the side that is going to become more positive, which is the side with the zinc solution. All right, and we're going to have several of those ions in there. And then to the opposite side, because we're losing positive charge, we're going to move, the potassiums are going to be moving in this direction. And we have some type of cotton wool. So the plugs are porous. So there is, you can allow for the motion of ions through the salt bridge. Let me just label that salt bridge. Now, when we actually do this, we will see that the voltmeter will actually register a certain value. And if we are actually doing this under standard conditions, it will register that the electropotential is going to be, or the potential difference is going to be 1.10 volts or 1.10 volts. All right, that is the potential that is happening. So that 1.10 volts can be used to, for example, give off light in the form of instead of having the voltmeter there, we can have a light bulb, or we can have a calculator, or we can have any of these other instruments, including our cell phones, that use electricity. So this is the principle behind any battery. All right, the principle is to separate the oxidation from the reduction. Now, let's see then the parts that we need. We need to have two half cells, one where there's oxidation, one where there is reduction. Two, we need to have some conductor to carry the charge. And three, we need to have a salt bridge, all right, that allows for electrical neutrality. And the salt bridge must contain some type of electrolyte solution, all right. The half cells are produced or are made out of the electrode, which is the metal, the actual solid metal, and then the solution of the metal ions. Okay, the site at which the oxidation takes place is called the anode. All right, and it's negatively charged because that's where you're giving off electrons. The site where the reduction is taking place is called the cathode, and it's positively charged. All right, an easy way to remember that, a little kind of thing, is an ox and red cat. All right, that kind of helps you remember that the oxidation is happening at the anode and the cathode, the reduction is happening at the cathode. An ox, red cat. All right, I guess it's a simple thing, but it does help you remember this. All right, so we see that now we have the overall reaction taking place. The zinc is giving off its electrons. The electrons are traveling through the wire. All right, they will come into the copper electrode and be transferred into the solution, where they will join as a copper 2+ ion to make copper solid, which will deposit on the electrode. On the other side, the zinc metal that lost the 2 electrons is becoming zinc ion, and so what actually is happening is that the anode, the zinc electrode, is becoming smaller because it's losing mass. It's dissolving into the solution. In order to keep neutrality, the anions will move into the site of the oxidation. The cations will move towards the side of the reduction. I don't know if you noticed that we can say this. The salt bridge anions move towards the anode. There's that similarity, and that's where the name of anode comes, because it attracts anions. The cathode attracts the cations, all right, the potassium ions in this particular case, and therefore that's why it's called the cathode. Okay, now the particular electrode potential or potential difference that you generate in this cell is 1.10 volts. We will talk about this in higher level of how this is calculated, but the reality is, if we were to switch over to table 14, all right, so here in table 14 we can see that the zinc 2+ ion plus 2 electrons to give you zinc metal has an associated potential of negative 0.76 volts, while copper 2+ ion plus 2 electrons to give you copper metal has a voltage associated, or a potential associated with it, of plus 0.34 volts. Now notice that the process that we are doing, or that's taking place in the reaction for the zinc, is not as it's currently written here, but it's in the opposite direction. We're going from zinc metal to zinc ion, and from the copper ion to the copper metal. So this process for copper is in the right direction. The process for zinc is going to be in the opposite direction. So we're going to correct for that when we're calculating. So let me show you a little bit more of how we would do this. All right. So we just go back to our data stream here, and we see if we actually have zinc going to zinc 2+ plus 2 electrons, the process said we're just going to take the number as it is there, all right, and this is for the anode, and we're just going to take the number exactly as it is. And for the cathode, I want us to take the process that we would be getting 2+ plus 2 electrons gives us 2 electrons, okay, what's going on? 2 electrons gives us copper, all right, and for the cathode, this process was plus 0.34 volts. Well, the reality is the potential for the cell is equal to the potential of the cathode minus the potential of the anode, always. And so it is E cathode minus E anode. That negative sign, what it's doing, it's correcting for the fact that the reaction at the anode is happening in the reverse direction. You could think about it being cathode and plus anode if you already changed the sign, but I just like to leave it like that. I don't have to think too much about it. I just do it once I'm entering the numbers. And so it's going to be 0.34 volts minus 0.76 volts, which gives us plus 1.10 volts, which is the result that we just had. All right, so whenever we look at a voltaic cell, there are several things to remember. The oxidation takes place always at the anode. The reduction takes place at the cathode. The anode is always going to be negative if you're talking about a voltaic cell, while the cathode is going to be positive. All right, so let's see what other values we can get for different metals. If we have different combinations of metals, we're going to get different values. And for the standard potential, cell potential, which is just how much electricity, what voltage potential difference is being established between the two electrodes when you are under standard conditions, when the solutions are at 1 molar concentration and where you're at 25 degrees Celsius. Okay, so let's look at this. If we use different metals, like for example, if we were to use copper and silver for our reaction, we can see, and let's go back again to our table 14 very quick. Okay, here in table 14 we can notice we have up towards the top the copper. It's higher than the silver metal, and so we know that the copper is going to be a better reducing agent than silver, and therefore be the one that becomes oxidized. This reaction, whichever one's higher up, is the one that the reaction is going to run in the opposite direction. All right, and the silver reaction will be this reduction that we see from silver ion plus 1 electron into silver metal. Also take note of the values that we have. All right, we have 0.34 and 0.80. Okay, so let's go back to our notes so we can actually continue looking at this. If we create this as we have it, this means that the copper, I lost my ion, okay, there we go, that the copper is the one that is going to be oxidized and is going to become copper 2+ ion, donating electrons to the to the silver ion to make silver metal. So this is the process that is happening. The oxidation is going to be like that, and the reduction is going to be this one here. So let's write those equations. The reduction is going to take place at the silver electrode. All right, the silver solution is going to absorb electrons and become and make metal, silver metal. All right, so this is the process that is taking place over here. We're going to have silver ion plus 1 electron going to silver metal. All right, and in the other side, we're going to have zinc losing 2 electrons and becoming zinc 2+ ion plus 2 electrons. Because this has to be balanced, the number of electrons must match on both sides. We are just going to multiply our equation times 2 on this side. So we have, we're going to make 2 particles or 2 atoms of silver metal for every atom of zinc metal that becomes zinc ion. Okay? Now let's look at all the parts and let's really highlight all of these sections that need to be used in order to make this. And so let me just get the highlighter pen, and okay, so we need to have an anode. All right, that is the site at which the oxidation is taking place. We need to have a cathode. All right, this is the site where the reduction is taking place. We need to have a salt bridge connecting the 2 half cells. All right, otherwise we will not have electrical neutrality. We need to have conductors or wires. All right, and normally we put a voltmeter, but we also can call it a load, something that will use the energy. Okay, so those are the 5 parts of a cell that must be included in your drawing if you actually have asked to draw a cell. All right, so the oxidation is taking place at the anode. The anode, because produces electrons, is negatively charged. The cathode is where we're doing the reduction, and it attracts the electrons, and therefore it is the one that is positively charged. All right, now the electrons are always going to go out the anode in a voltaic cell, and in this particular case I'm going to put 2 electrons as opposed to just 1, since we're using 2 electrons, and I'm going to put 2 electrons over here too, and they're going to travel. And again, I want to see if I can get my pen to show you which way they're going to be traveling. I'm going to do it in some kind of fun color. All right, they're going to be traveling in this direction and into, all right, out of the copper and into the silver, and in the silver they will come into contact down here. The electrons come into contact with the silver ion to deposit silver metal onto the electrode. The electrode is just the name that we give to the piece of metal that is in contact with the solution. All right, so the flow of the electrons is always going to go from the anode to the cathode in a voltaic cell. Now you see the value that has been read by the voltmeter. If we look at this very quickly, remember we said E naught for the cell is equal to E cathode minus E anode, and in this particular case it was plus 80 volts minus plus 36 or 34 volts, which gives us plus 0.46 volts as the overall value for the amount of voltage or potential difference being generated by this cell. We can set up any arrangement of cells. I tend to like to write my cells in such a way that the anode is on the left side and the cathode is on the right side. So for that, you always have to go again back to your table 14 when you're checking for the metals. Check which one is higher on the table so you know which one is the one that is going to be oxidized, which one is the one that's going to be in the opposite direction. So if we were to choose iron, for example, here, okay, all right, here iron, and we were reacting it with lead, well, the iron would be in the anode and the lead would be in the cathode because it's higher. The iron is higher than the lead. And again, so anything that is higher up is going to be a better reducing agent. A reducing agent is the species that gets oxidized. All right, so anytime, that's the one that you're going to be putting in the anode, whichever one is higher in that position. The value that you get for a cell is always going to be positive. So if you calculate something and it gives you a value that is negative, it's because you have switched the anode and the cathode. All right, so that is voltaic cells at the standard level. Higher level, we'll do a second little video talking a little bit more about calculation of the potentials. All right, okay, wonderful, thank you.